Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion related to this course, Introduction to Electronics. And from today, we begin our discussion related to amplifiers. So the first statement is regarding the importance of amplification. And, this particular statement that amplification is the heartbeat of electronics. What this means is that if for some reason amplification were to stop, then the whole of electronics will grind to a halt. Just like the heartbeat is essential to our survival, similarly amplification is essential to survival of electronics. Almost everything that we have requires amplification to work properly. And so it's a very important part of electronics, and let's see how we can build amplifiers using transistors. All right, so there are various kinds of amplifiers. We may be interested in amplifying a voltage or a current. And in this particular course, we'll confine a discussion related to voltage amplification. And so we have this amplifier here and a three-terminal device here, one common terminal. So the input is applied over here, Vi, and the output is taken at this particular place here. And so the output is equal to basically the shape of the output is same as shape of the input, except that the output is a magnified version. So V0 equal to G times Vi. And the important point to note is that G is constant. G does not depend on, let's say, the input voltage, or ideally it does not depend on frequency. And the gain, G is the gain, the voltage gain is greater than 1. And so note that this is a linear relationship. V0 equal to G times Vi, and linearity is important because we want output to look exactly like the input in terms of its shape, but with a higher magnitude. And if there were any non-linearity, then the output would become distorted. And so this linearity, this linear relationship is important. And of course, we want gain to be greater than 1. So how can we build an amplifier like this? Okay, so this is the objective, that we want to build a voltage amplifier with a gain which is constant and greater than 1. So suppose, just for the sake of discussion, we have a three-terminal device available to us. A three-terminal device shown over here, and it's a linear device, and it's a unilateral device. Unilateral meaning the input will affect the output, but the output can't affect on anything on the input side. Okay, meaning that if I change the output voltage, let's say, it cannot alter the current flowing into the circuit, input current flowing into the circuit. And we have seen that when we have, this is a two-port device, we could represent it in this particular form here, in the form of, you can see a H parameter kind of a representation here. And so from the output side, we are representing it as a GMVI times R0 here. And from the input side, we are representing it as simply a resistor. And note that in a two-port network, in a two-port representation, we would have had a term here also, which would have depended on the output voltage. But because we have said that this is a unilateral device, so there is no term, there's no element which depends on the output voltage on the input side here. So the input side can be simply represented by a resistor Ri here. And we are saying that this is a linear device, so Ri, Gm, R0, these are all constants. And therefore, the relationship between current and voltage here, or between I0 and Vi, these are all linear relationship here. So this three-terminal unilateral linear device could be represented in this particular form here. Right, so and we can attach some terms with it. Ri, for example, we could call it as an input resistance, because note that if you look at this particular circuit, Ri is nothing but the ratio of Vi by Ii here, and whatever current is entering, and the voltage applied here. So because this is the input side here, so the ratio of course is Ri here. So we call it the input resistance. transconductance GM is, note that I0 has two components. One is due to R0 here, which is because of the voltage V0 itself. And that is what we call as the output conductance. The ratio of 1 over R0 is G0 is called output conductance here, which makes sense that this is a resistor connected across the output terminals here. But this component of the current I naught equal to GMVI, so it depends on the input voltage here, and that's why we call it the transconductance here, because note that the units of it, this particular one, because it relates current to voltage here, so the units is conductance, but because it's related to voltage applied across a different pair of terminals, we call it a transconductance. So GM is transconductance, R0 is output resistance or output conductance, and Ri is input resistance here. So if we had a 3-terminal unilateral linear device, we could represent it in this particular form here. We could take that particular device and experimentally measure Ri, GM, and R0, all these parameters we could measure. And if we had knowledge of what is inside, perhaps we could have determined expressions also. So our goal is to build a voltage amplifier. This is a voltage amplifier here. And voltage amplifier meaning that if I take a source with some resistance Rs here and I attach a load here RL, I should get V0 by Vs. This is my signal. V0 by Vs should be greater than 1. So let's try and build this amplifier using this 3-terminal device that we thought of, this 3-terminal unilateral device here. So what we'll do is we'll take this, let's build it up. So the whole thing is an amplifier here, and let's take this particular block using which we are building an amplifier and replace it by this particular 3-terminal device here. So this is the circuit that we get here. We simply take this out and substitute it here. So Rs, Ri, GMVI, R0, RL here. And it's easy to analyze this particular circuit. We know what is Vi. This is a voltage divider here. Vi is Ri plus Rs into Vs here. And output voltage V0 is nothing but this GMVI current flows through a parallel combination of R0, RL. So V0 is minus GMVI, R0 parallel RL here. And we can combine them together to get AV, the voltage gain. The voltage gain, sometimes we'll use a symbol G here, and sometimes the voltage gain AV equal to V0 by Vs. Minus GM, some terms have been rearranged, GM R0, RL by R0 plus RL here, Ri by Ri plus Rs here. And so what this expression tells us is, if you note that this second term and the third term are less than 1, or the maximum value could be 1 if RL is much larger than R0, and similarly Ri is much larger than Rs. So the maximum value here is basically 1 here. And therefore, if you want to get a gain, it is essential, minus sign just ignores the 180-degree phase difference between the output and the input here. So if you look at the magnitude of the gain will be less than or equal to GMR0, the first term here. And therefore, a necessary condition for obtaining voltage amplification is GM into R0 must be larger than 1. So this 3-terminal device that we had, Ri, GMVI, R0, if it obeys the condition GM R0 is greater than 1, then we could use that particular device with some Rs and some RL, and we could obtain a voltage amplification. We could get gain larger than 1 here. So this is the essential condition. If we had a 3-terminal linear device and we wanted to build an amplifier using it, then it's essential that its transconductance multiplied by output resistance must be much larger than 1. Note that the larger this quantity here, GMR0, the larger the gain that we may be able to obtain. And so GMR0 must be much larger than 1, or we could arrange it and write it as GM must be much larger than 1 over R0, which is nothing but the output conductance here. So what we are saying is the following. If we want to build an amplifier using a 3-terminal device, then a necessary condition is that transconductance must be much larger than output conductance. GM here must be much larger than 1 over R0. So that's a necessary condition for obtaining the voltage amplification. And we call such a device a transistor, a device which exhibits transconductance significantly higher than its output conductance here. Okay, and so that's the device we call as a transistor here. So that's one of the essential characteristics of a transistor if we want to use it for amplification here. So transistor, if you go back in history and look at, for example, the interpretation of the word transistor, one could write it as transresistor or transresistor or a transconductance. So what we are seeing here is that, we just said that transconductance is much, much larger than the essential characteristics of transistor is that transconductance is much, much larger than output conductance, which means what? That current I0, transconductance is nothing but the dependence of I0 on Vin. And what is the output conductance? Is the dependence of I0 on V0. So what we are saying is that I0 is much, much more sensitive to Vin as compared to the sensitivity of I0 to V0 here. Okay, so that's the essential property here. Ideally I0 would not depend much on V0 at all, but I0 would depend, would be quite sensitive and would depend significantly on the applied voltage here. So that's the essential characteristics of a transistor. So it's a device which exhibits transconductance as its prominent characteristics, transconductance or transresistance as a prominent characteristics. All right, so then let's proceed with this kind of a device. So let's assume that we have a device with a GM times R0 much, much larger than 1. And in ideal case, if you're thinking of an ideal amplifying transistor, then what we would like is that R0 is infinite. In that case, I0 has no sensitivity on V0, but I0 of course has significant sensitivity to VI here. So if we were to think of an ideal transistor, that would be a device with R0 equal to infinity. So let's build that ideal transistor here. So let's remove R0 here. And so this is the device that we get here. And we saw that if we want to build an amplifier using this, then this is the expression that we got here, right? Minus GMR0 RL by R0 plus RL here. Now, the fact that we have chosen R0 equal to infinity, so this term goes away, and we are left with Ri by Ri plus Rs here. So Ri is also an element of transistor. So again, so we are thinking of building an ideal amplifier. So an ideal amplifier would be, if we look at this particular term, where Ri is much, much larger than Rs. Whatever Rs source resistance you connect, Ri is much, much larger than Rs. And that condition can be arranged if we make Ri equal to infinite also. Right? So if Ri is infinite, then no matter what source resistance I connect in series with it, that would obviously be much smaller than it, and this factor would be practically equal to 1 here. So let's put Ri also to be infinity here, input resistance to be infinity here. Then our gain will simply be equal to AV will be equal to minus GM times RL here. Okay, because this term we've already taken R0 to be infinity here. So this R0 and this term cancel each other. We get minus GMRL here. So the gain of such a device is minus GMRL. Voltage gain is equal to minus GMRL. Note that we are talking about voltage amplification. We should not forget that for a device to be called a transistor, or for an amplifying device, or for something to be called an amplifier, it's essential that we must have power gain. And we can see that when we are choosing an ideal transistor with Ri equal to 0 here, Ri equal to infinity here, and R0 equal to infinity here, we know that the input current is 0 then, and there is no input current here. So from the input side, we are not drawing any power from the input source here. But output, of course, there'll be power delivered to the load here. So there is a power gain inherent in our design here. So an ideal 3-terminal device for voltage amplification is what? Well, it's a unilateral device with infinite input resistance infinite output resistance, and simply has this particular term here, a transconductance term here, GM. So that's an ideal device here. And if we were to describe it graphically, the fact that I naught has no dependence on V naught, so we can I naught, if we were to plot I naught versus V naught, so we call this the output characteristics of the device here, I naught versus V naught. So what we would see is a constant line here. For depending on different values of Vi, we'll get a current I naught, some current which is Gm times Vi1. For some higher values of Vi2, we'll get Gm times Vi2. For some other higher values of Vi3, we'll get Gm times Vi3 here. So output characteristics, I naught versus V naught, would look like this here for an ideal transistor. And the transconductance characteristics, this is the other thing that we can plot here, I naught versus Vi. So I naught versus Vi is a linear relationship like this here, Gm times Vi here, right? And input current versus Vi, well, we have infinite resistance, so input current is 0 here. So graphically, if we want to describe an ideal transistor, it would look like I naught versus V naught. It looks like a current source here. Note that there is a current flowing. If you look at the output side is like a current source, but dependent current source here. So I naught is independent of V naught, like a current source here, constant characteristics here, and I naught is linearly dependent on Vi in this particular manner here. So that's an ideal transistor. And if we had this ideal transistor, then very easy to build a amplifier, right? So the amplifier, all you need to do is take a ideal transistor, put one terminal to ground, attach the input, the source, the signal that you want to amplify to its input, and connect the output to RL. And well, how do we analyze this? Well, the ideal transistor's model is shown over here. So take this ideal transistor, this block out, replace it by this particular piece of circuit. So you'll get this one here, overall circuit of the amplifier, and it's easy to see that AV equal to V naught by Vs is minus GMRL. And therefore, all you need to do is, given a value of GM, all you need to do is connect a suitable value of RL, and you'll get a gain which is greater than 1. The only trouble is that there is no element which has this, that's why we are calling it ideal. There is no element which has this characteristics of ideal transistor here. And so gradually let's introduce some non-idealities into our transistor. So this is ideal transistor. I naught is independent of V naught, only depends on Vi1. And this is what is shown over here, linear relationship. So let us suppose that we had a device like this here, some hypothetical device, device X, whose output characteristics I naught versus V naught still looks just like the ideal one. But the other characteristic, the transconductance characteristics, I naught versus Vi. So I naught is 0 up to a threshold point here. So there is a threshold voltage kind of a thing, V alpha. And after that, it's a linear relationship. So this is the non-ideality. And I naught is not conducting for negative values of Vi. I naught is only conducting for positive values of Vi. And that too, after a threshold value here. So that's a non-ideality. If we compare the two, we can see that this is a non-ideality that is there here. So the issue before us is, if we had this ideal transistor, making an amplifier was very easy. Just connect the source, the signal to its input, and connect the load, the resistor to its output, and we had an amplifier which was ready. But now that we have a device like this, device X, and let's say that's a new kind of a hypothetical transistor, the issue is how do we make an amplifier using device X? The next thing is, we'll see later on, suppose we have a device Y, which has not only this non-ideality, but its output characteristics is also not like the ideal characteristics here. We see that it behaves like an ideal characteristics for voltages larger than Vsat. So whenever V naught is greater than Vsat, we see this constant region here, just like the ideal. But for V naught less than Vsat, well, we have zero current and we have no current in the, for negative V naught also. So we have now two non-idealities. We have a non-ideality in I0 versus Vi characteristics, and we have non-ideality in I0 versus V0 characteristics. And the issue is, if we are given a device like this, how do we build an amplifier here? And the reason why we are doing it is the device Y we will see here is quite close to how a MOSFET looks like here, right? So a MOSFET would have something looking like this particular one here. So before going to a MOSFET amplifier, let's look at these simplified amplifier designs using a device X, which has only one kind of non-ideality, and then device Y, which has two kinds of non-ideality. And then we'll go on to a real MOSFET. And then the design of an amplifier using a real MOSFET will make a lot more sense. All right, so in this particular lecture, let's concentrate then next on how do we build an amplifier using a hypothetical transistor with the characteristics given by these two graphs here. Okay. All right, so this is our device X here, right? So output side is fine. I0 versus V0 is fine. I0 is equal to 0 for Vi less than or equal to V alpha. So we are calling it V alpha as a threshold voltage kind of a thing. And for I0 greater than V alpha, for Vi greater than V alpha, so this is equal to some Gm, Vi minus V alpha. Okay, so it's a linear relationship. All right, so these are the ideal characteristics, right? So we have to take care of this one here. Somehow we have to manage the non-ideality that we see here. So, all right, so this is, suppose we just did what we did using a ideal transistor. In an ideal transistor, we simply connected the source, Vs, and we connected an RL here, right? And can we do that now with our device like this here? Well, note that our non-ideal device with a characteristic like this will now not work, will have problems working as an amplifier. So let's look at this. I0 versus Vi we are saying is in this form. For the sake of discussion, let's take V alpha equal to 1 volt here. The threshold point is 1 volt here. And Gm let's take as 0.01. And let's put some load resistance of 1 kilo ohm. And the signal that we want to amplify will be some small signal here. And just for the sake of discussion, let's suppose we could have taken any small value here. Let's suppose it is 0.5 volt sine omega t. So note that we are applying this Vs signal here to the input, and we have these characteristics I0 versus Vi given over here. So Vi is varying like this here. Note that in this case, when I'm drawing a sinusoid like this, so what I'm doing is on this axis is Vi, and temporarily when we are talking about the sinusoid, we are taking the y-axis as the time axis here. Okay, so when V0 is when my Vs signal goes like this here, so it will reach a maximum value of 0.5, and then it will go a minimum value of minus 0.5 here. And so what we note here is that if we directly take our signal Vs, apply to the input, then it all the time is lying in this particular region here, in this dead zone region here where there is no current here. And obviously then no current would flow in my output, and there will be no output voltage at all. So I0 will be equal to 0 and V0 will be equal to 0. So my amplifier will not work. I'll get nothing at the output here. So the issue before us is that we don't have an ideal. We said ideal transistor is not available. What you will have are elements with all kinds of non-idealities. So suppose we have a non-ideality like this here. Then if we simply connect an input to this kind of a non-ideal transistor, well, it's not going to amplify. Note that in this case it is 0.5 volt, and we may be talking about signals which are even weaker, maybe 1 millivolt here. So it would be very close to the origin here, and therefore the current is 0 and the amplifier will not work. Now there's a simple solution to it. We note that for an amplifier to work, I0 of course has to work here. I0 has to respond to Vi. Right, so that's how we are building an amplifier. This current I0 has to respond to Vs in a linear manner. So I0 has to respond to Vs, and when this I0 flows through RL, it will develop a V0, and therefore V0 will respond to Vs. And if relationship between I0 and Vs is linear, relationship between V0 and Vs will also be linear. So we'll get some linear voltage here, which will we'll get a voltage here which will look exactly like Vs. And if my GM and other things are properly chosen, then we'll get amplification. So we want the current to respond to Vs. So somehow the input is very weak. The input lies here. So we have to shift the input to this particular region here. We have to shift it to this particular region because that's where the current is flowing, right? So what we do is, we can see that it's easy to shift the input here if we add a voltage, a DC voltage here. So what we do is, we don't apply Vs directly to the input here. We apply Vs and in series with a bias voltage here, a series with the bias voltage here. And we note that the bias voltage, because this Vs will be, it has both, note that it has a positive component and a negative component, and it's a very weak signal. Normally it would be a very weak signal. So obviously, to have current flowing here, I must have a bias voltage which is greater than the threshold voltage here, right? So we must apply a bias voltage larger than threshold voltage here. So once we do that, note that what we are doing is that for the moment, assume that Vs is not there. So then we are at this particular point here. If Vs is not there, then we are at this dotted line. We have applied a bias voltage Vb. So at this operating point here, we are operating here. Then when you add Vs to it, what will happen is that the net input voltage here, Vi, will increase a little bit beyond Vi and then will decrease a little bit below Vi, right? So this is how my actual input voltage will go. For example, we have applied 0.5 volts. So if Vb is, let's say, 1.5, so this will go from 1.5 to 2 here, and then it will go from 1.5 to minus 1 volt here, okay? So as this voltage, note that we are biasing it at Vb. Now as we superimpose this sinusoid here, so as this voltage increases here, what would happen is the current would increase here, right? So that's what we are showing, the current increases here. And as the voltage here decreases, the current also decreases, okay? So that's how, so I0 will now, so I0 will respond to these changes here, right? So I0, if you look at the output current will have a DC current here, right? So if there is no Vs there, you applied Vb here, so corresponding to some Vb, there would be a DC current flowing here. But then the moment you add this source here, Vs, it modulates the input voltage here, increases and decreases, and corresponding to changes in Vi, there are corresponding changes in V0 here, I0 here. So the output current will have a sinusoidal current here. If this is sinusoidal, the output will have sinusoidal. If this were a speech signal or a video signal, the output will be exactly like that speech signal or a video signal here. And so besides the DC current, it would have that extra signal component here. And therefore the output voltage will also have that signal component here. Okay, so V0 is nothing but, we can see here, I0 flows in this particular direction, so V0 is minus I0 RL. So V0 is directly, if you ignore the minus sign for a moment, the phase change, V0 is directly proportional to I0. So by this means, we will be able to amplify our signal Vs, provided we have a DC signal which biases my transistor, hypothetical transistor at this particular place here. So this is an important point, that when only a part of device characteristics is suitable for amplification, then we need to push the device into that region by applying suitable bias voltage here. This process is called biasing. So all transistors that we have are non-ideal transistors. So biasing is an essential element of all amplifiers here. So the goal of biasing is what? The goal of biasing is to, so what happens is, non-ideal transistors would have a region in their operational characteristics where they are suitable for amplification. And therefore the purpose of the biasing voltage is to push the transistor into that particular region here. Okay, so that's what we are doing. The transistor is capable of amplification here. This is where the output current responds to Vi. And therefore we are applying a bias voltage Vb to push our transistor in this particular region here, to push it in this particular region here, and then we are applying the signal. The signal is on top of the other one, and now the transistor responds to that particular signal and amplifies it here. So the next issue is, fine, so we need Vb to operate in this particular region here. The issue is, how should we choose Vb? What should be a suitable value of Vb? Okay, and so let's look at two cases here, right? So we have a signal Vs is 0.5 sin omega t. Suppose we apply a bias voltage of 1.2. Okay, So note that our threshold point is 1 and we apply a bias voltage of 1.2, right? So we are in this particular region here. But now what will happen is we are in this particular region, but in addition to VB, we have this VS here, right? So let's see what happens here. So this bias point, so in the absence of the signal, we are applying a bias voltage. So we are operating at some particular point here. And we have several names for it. We call it the bias point, the operating point, or we also call it the quiescent point here. So this is the place where we are operating our transistor here with a input voltage at 1.2 and the corresponding output current is, let's say, 2 milliamperes here. Okay. So let's apply our signal also now. So now when we apply a signal, the total input voltage is shown over here. So when you don't apply any signal, then of course the voltage is 1.2 volt. We're applying 1.2 volt. When you apply a signal here, which is 0.5, so it will go from 1.2 to 1.2 plus 0.5 here, so 1.7 here, and 1.2 minus 0.5 here, and so it goes to minus 0.7 here, right? So it goes both in this particular region here and it goes in here. So it goes to 1.7 here and goes to minus 0.7, right? So that's the input voltage here. That's the next input voltage here. Okay. Now note that this is the characteristics of my transistor, right? This is the characteristics of my transistor. So when we look at the positive cycle here, when it starts from 1.2 and it goes to 1.7 here, so you're starting from 1.2 and you're going up here. So obviously there is a current flowing here, increasing current flowing here, and increasing current flowing here, and therefore the V0 will also respond. So in the positive direction, it responds here, right? So there is a current like this here, it goes here. But when you go in the negative direction, so as you start from 1.2, and as you go in the negative direction, what happens is till 1 volt there is a current flowing here. So till about 1 volt there is a current here. If you look at it, you start from 2, so this is the positive cycle here, and then when you go in the negative direction, there is a current flowing here, but then the voltage will reach 1, and after that current is 0. So I0 will be 0 here. So now note that I0 is not responding to the signal here. The signal has all this component here, but I0 is not responding here. It is clipped. It is 0 here because you are now in this particular zone here. And note that V0 is nothing but proportional to I0, right? So if I0 goes like this here, V0 will also follow that particular part here. V0 is minus I0 RL. So one of the main goals of amplification is that V0 should look exactly like Vs, but a magnified version. Now we are seeing that V0 will look like this here, and therefore V0 is distorted. There's a part of the output waveform which is clipped here. It is clipped here, right? So output voltage is distorted. So this is I0 and V0 is minus I0 RL. So V0 will look like this here, not because of minus I0 RL. So look at how V0 looks here. So the output is clipped here. Now, which means output is distorted. So it means my amplifier is not working properly. And what is the reason that it's not working properly? Well, we have not biased the amplifier properly. We can very easily see that 1.2 volt is not adequate. Because with 1.2 volt, my transistor, when I'm applying Vs, is entering that zero current region here, or the dead zone region here. And that's why we are getting a distortion in this circuit. All right, so we need to choose, what we are saying is we need to choose a proper value of biasing voltage here. 1.2 volt is not adequate. All right, somebody chooses 1.8 volt, realizing that you need to be away from the threshold point here of 1 volt. So somebody chooses 1.8 volt here. Okay, so with 1.8, with maximum 1.8 plus 0.5, so you'll go to 2.3 here, and minimum you'll go 1.8 minus 0.5, so you'll go 1.3 here. And 1.3 is clear of the threshold point of 1 volt. So we are fine here. So that's the input. And so we are away from, even when we apply the signal, we don't go into this particular dead zone region here. And I0 goes fine here. And V0 also goes fine here, right? So everything seems fine. V0 is just like Vin with a phase change. And it's a amplified version of it. Note that this is 0.5 here, and the output signal here if you subtract the DC part here, so ignore the DC part, there is a minus 8 volt DC. The sinusoid part here, you can see is an amplified version of the sinusoid here. So there is so it seems to be working fine, except that there is a problem here. And the problem is that, it's not just the amplification which is important for us. Power is also important. We don't want to, many of these amplifiers will be part of portable devices, and we do not want to unnecessarily waste power. So assume for a moment that Vs is not there. So if Vs is not there, signal is not there, then we will have what? We'll have 1.8 volt applied to my transistor here. And 1.8 volt will cause 8 milliamperes to flow. Note that the DC value is 8 milliamperes to flow. And this 8 milliamperes of current will flow in the output part here. And this 8 milliamperes of current will of course generate a 8 volt here. Or 8 milliamperes of current is flowing through 1K. And therefore there is a power dissipation in this load. And this power dissipation is useless because our interest is basically in the signal here. Our interest is in the sinusoidal signal here. And our interest is in the power associated with the sinusoidal signal here. This is a DC voltage here. Minus 8 volt is a DC voltage here, and minus 8 milliamperes is a DC current here. So there's a power which is dissipated in RL, and that power is waste, right? And so that is a problem for us, and that's something that we don't want to do. So we don't want to unnecessarily waste power. So the question, and note that instead of 1.8, we could have biased it at 2 volt also, and that would have also worked fine in terms of amplification. But the 2 volt biasing point would have caused even larger current to flow and larger power dissipation to occur. So the issue is, are we unnecessarily, is it really necessary that we bias it at 1.8? Because the lower the biasing point we bring, the smaller the DC current and the smaller the power dissipation, right? So that's the other issue. We don't want unnecessary power dissipation. So in that case, maybe what would be the optimum biasing point? Well, 1.5 may do the trick for us because the voltage is Vs is 0.5 sine omega t here. So if we take 1.5 here, bias point, and Vs is 0.5 here, so then this input will go from 1.5 to plus 0.52, and then here it goes to 1. So that's how input looks like. And I naught will also go like this here. Note that in the negative cycle, I know the effective input voltage is reaching 1 volt here, and I naught is falling to 0, and therefore we get an output which is fine here. Note that we cannot apply anything less than 1.5 because then we'll, for a part of the cycle, we'll go into this dead zone region here and we'll start getting clipping here. Even 1.5 volt, realistically speaking, we should not do that because we know that there are tolerances in the circuit. What if, let's say my transistor's threshold point is not 1 volt, but it is 1.1 volt? Then 1.5 will cause a clipping to occur in my circuit here. So we have to always give a safety margin. But if we ignore those particular considerations, then we can see that 1.5 volt would be an optimum biasing point. 1.8 volt was unnecessary and 1.2 volt was too low. The other point is, note that, so we apply 1.5 and we apply a signal and we're getting a current here, and the current has a DC part and a sinusoidal part. DC part is essential because we need to bias it at a DC voltage here, otherwise the whole thing will not work. And so I naught has a DC plus an AC component, and output voltage also has a AC and a DC component here. And this DC value is something that I'm not really interested in. See, note that I'm interested in the speech or the video signal here. So to the output, I want to deliver only the signal here. I don't want to deliver a DC part there, right? So how do we get rid of the DC voltage here? So whenever you want to get rid of the DC voltage, we realize that capacitor acts as blocks any DC signal, right? So we could use a capacitor here. So a simple thing we may think, well, let's put a capacitor. We don't want a DC current to flow through my load, and we want only the AC part here. So let's put a capacitor here. So the capacitor is going to block the DC part here and But note that the moment I put a capacitor here, well, the capacitor, the current then, because when you apply 1.5 volt here, right, you require when you apply 1.5 volt here, assume for a moment that there is no signal here. So when you apply 1.5 volt, you would like to operate here. You would like 5 milliamperes of DC current to flow, right? So if you put a capacitor directly here, where would that 5 milliampere current flow? There is no path for the current here. So your transistor would then be forced to operate at I naught equal to 0, right? So something will happen where because it's some kind of a ideal characteristics that we are building. So with a 1.5 volt, we require I naught to flow. We require I naught of 5 milliamperes to flow, but there's no path for this particular current to flow here. So we have to modify this particular circuit. Of course, the sinusoidal part here, the sinusoidal part can go through the capacitor if we choose the capacitor value properly, such that the impedance of the capacitor is very small compared to RL. The sinusoidal part can go. But for the whole thing to work properly, first of all, we need to provide a path for this 5 milliamperes DC current to flow. And so that's why we add this particular resistor here. We add a resistor RD here. So now what happens is, when we forget for a moment the signal here, when you apply 1.5 volt here, it requires 5 milliampere current to flow here to operate at this particular point. The transistor needs to operate at this particular point here. And this RD provides a path here. RD will provide a path for this DC current to flow here. Okay. So this is so when we are looking at, so what we are finding is that in general, when we build amplifiers, we'll have biasing voltages and which are DC in nature. And the signal for us would be whether it's a speech or a video, and for simplicity, for discussion, we'll take it as a sinusoidal. So it's an AC signal here. So analysis of our amplifiers, we can break it up into a DC analysis, and we need to make sure that the DC voltages are appropriate. There is a path for DC currents to flow here. So we do a DC analysis here, where we remove, note that the whole thing is linear, so we can use superposition. So we remove Vs here, and we look at how a circuit behaves under DC condition. So we keep 1.5 volt here. And under DC condition, the capacitor will be open circuit, so this part of the circuit is not there. So we have a DC circuit here that gives us what is the output current, DC current flowing here. And then we can talk about what happens with respect to the signal. So with respect to the AC signal. And then we'll remove the DC here. So we'll remove the DC here. So the AC signal is here. And we are saying that the capacitor will act like capacitor is chosen such that it acts as a short. Almost like a short of very low impedance path. So we'll ignore the effect of the capacitor when we have an AC signal. So with respect to this signal, the circuit looks like this here. We have this particular transistor, we have RD, and we have RL here. Right? So analysis of such circuits could be broken into a DC analysis and a AC analysis of the circuit, or a signal analysis of the circuit. Okay, so how do we do the AC analysis here? So DC analysis is straightforward. 1.5 volt is here. So we go 1.5 volt here, and we, from this particular part of the circuit, we can read what is the current here, 5 milliamperes. So 5 milliamperes will flow here. And if we are given the value of RD, then we'll know what is the output voltage here, DC output voltage, DC voltage here at this particular point. So DC analysis is straightforward. How do we do the AC analysis? Well, okay, so this is the AC circuit here. And note that for the AC part here, so we apply our sinusoidal signal here. From the input side, it looks as a open circuit here because input resistance is infinite. This is VI here. And from the output side, note that from the output side, we can represent this characteristics as GM when we are in this region here, GM VI minus V alpha, right? So the current I naught is a function of V in, I naught is GM, VI minus V alpha, for VI greater than V alpha here. So we can describe it as a dependent current source here, VI minus V alpha here. And of course, there's an RD and there's an RL here. So that's the circuit that we need to solve here. And so this is our basically transistor model. And if we look at the transistor model here, if you look at this particular term GM VI minus V alpha here, you can break it up into two current sources. One is GMVI, which is shown here, and the other one is minus GM V alpha, which we can write it like this, GM times V alpha here. Now note that our interest is in basically the sinusoidal part here. The sinusoidal current, the sinusoidal voltage, the sinusoidal output voltage here, AC analysis we are doing. Now, if you look at this, V alpha is a constant and GM is a constant. So this is a DC current. And so when your interest is in sinusoidal, you can ignore this particular part here, right? You can forget about this particular part here and just keep these parts here. So this is the circuit that you need to solve here. VS applied here and GMVI here and RD parallel RL here. And the voltage gain will then be equal to V0 by Vs is minus GM RD parallel RL. And this is what we can call as the AC model of the transistor here. That when we are talking about the AC or the signal part here, my transistor can be looked upon in this particular manner here. Note that V alpha, GM times V alpha is a DC component and therefore you can ignore it. You can remove it here. So this is the AC model of the transistor here. All right, so what we have then is that if we are given a non-ideal element like this here, then we can build an amplifier by biasing it through this DC voltage here, VB here. And if we don't want any DC voltage at the output, we can use a capacitor here, provide a DC path through RD here, and connect a load here. And thereby we've made an amplifier using a non-ideal element like this here. And note that the purpose of all of this here, VB and RD and all this capacitor here, is basically to make the non-ideal element appear as an ideal element to this particular source here. Okay, so now if you think of all this thing in the block, this whole circuit in the block is like an ideal transistor, right? So we said an ideal transistor is what? You simply attach a Vs to it and you connect a load to it and it amplifies. Well, now we have a non-ideal element here, but with non-ideal element, with some biasing, with some RD, with some capacitor here, if we look at this particular block, the purpose of all this is to make the non-ideal element behave like an ideal element here over a certain voltage range here, right? So to the source Vs here, this whole thing appears like an ideal transistor element here. You're simply attaching a Vs and you're connecting a load, a resistor RL, and you're getting amplification. All right, so the whole purpose is that of biasing and all this arrangement that you see here is to make your non-ideal element appear as an ideal transistor to the input and to the load here. Now, there's another part here. What happens if both DC voltage source and signal source have one terminal as AC ground? So here we had simply connected the signal in series with the biasing voltage. So many times what we have is the biasing voltage has one terminal ground and the signal also has one terminal ground. Many times we encounter situations like this here, and therefore connecting them in series is not possible in this simple manner here. If we connect VB on top of VS like this here, then because one terminal is always connected to ground, one terminal is always connected to ground, then if we do that, then the signal gets shorted, right? So if we just put VB on top of VS here, the signal will get shorted here. So we can't do that here. So we need an alternative arrangement, and one solution to this is the following here. So we take Vs and we use a capacitor here. Now again, we will choose a capacitor such that the capacitor at the frequency of interest, the capacitor will act like a short. It's a low impedance path here. So we take Vs and connect it through a capacitor like this here. And we take a biasing voltage VB, one end of both of them is ground here, and we connect it through a resistor here. And so the goal is nothing but Vi should be sum of VB plus Vs. And what we are claiming is that through this arrangement, Vi will be equal to Vs plus VB here. So let's see how that happens here. Okay, so this gives us Vs plus VB here. So let's look at this particular part of the circuit here, right? Now, as far as DC is concerned, so when we look at DC, capacitor acts as a block. So we can see Vi will be nothing but, note that the input, no current flows at the input here, right? So Vi is equal to VB. And then when we look at the other source here, so it's a linear circuit, so let's look at superposition. So when we look at the other source here, Vs here, The capacitor acts as so we get this particular part of the circuit here, VB, we will short it, and the capacitor acts like a short here, so VI will be basically equal to VS here. So what will be the total VI? VI due to VS and VB will be equal to VS plus VB here. So we are able to sum the bias voltage and the sinusoidal signal here through this particular means when one terminal or both of them is ground here, right? So note the role of importance of RB. Even though no current may be flowing through RB in this particular case here, but RB is essential. If you don't have RB, then think about what will happen. Okay, so RB is essential here. RB or RD biasing resistor essential here. So our final amplifier schematic is like this here. So when we have a non-ideal element like this here with a threshold point here, below threshold the current is 0 here, and from the output side it looks like an ideal one here. This is the amplifier schematic that we obtain here. And we should realize the role of each particular element here. The role of biasing is to push the amplifier in this particular region here, right? And the role of RD is to provide a DC current path. The capacitor is there to block any DC voltage from going to the output. And of course, there's a load resistor here. And we are using a capacitor here in this particular arrangement to obtain VI, which is the sum of VS and VB here. All right, so let's stop here, and the next lecture we'll look at another device with a non-ideality in this output characteristics also, and we'll see how to take care of that as well.